Hello everyone. Today we are going to understand the concept of symmetric charge distribution. We use the concept of symmetric charge distribution in discussing the application of Gauss law. And let us discuss Gauss law in brief. So from Gauss law, we can write total electric flux. Okay, so this is total electric flux through closed surface or Gaussian surface. Okay, so this equals surface integral of electric field, okay, throughout the closed part or closed surface equals 1 by epsilon naught or epsilon 0 times the charge inside the closed surface or Gaussian surface. So we can rewrite this equation in this way. Okay, so I'm changing the color. Surface integral of electric field throughout the closed surface equals Q by epsilon naught or epsilon 0. Clear? So this is charge inside the closed surface or Gaussian surface. Okay, and this is vector area. Okay, so this is elementary area of the closed or Gaussian surface. So we need to note this and let us call it equation 1. Now we need to understand what is closed surface. Okay, so let's understand what is closed surface. So the closed surface divides the space. Okay, divides the space into inner and outer region, and we cannot move from one region to another region. That is, we can write we cannot move from, let's say, inner to outer region without penetrating the closed surface. So we need to understand this, and always remember we apply Gauss law to closed surface called Gaussian surface. Okay, and Gaussian surface is not a real surface, it is an imaginary surface. Clear? Now we can simplify, okay, equation 1 and determine the electric field. Okay, so on simplification of equation 1, we can calculate or determine the value of electric field. So for that, okay, for this we choose or select a surface. Okay, in such a way that we can take the advantage, okay, advantage of symmetric charge distribution. Clear? So we select or choose surface, that is closed surface, in such a way that we can take advantage of symmetric charge distribution. So we can take electric field, okay. So if we look into this expression or this, okay, so we can take electric field out of the integral, okay, of, let's say, equation 1. So I'm indicating this as 1 of equation 1, and determine it, okay. So our aim is to select or choose a surface, okay, which satisfies one or more of the following conditions. 1, electric field on the surface must be constant, okay. So I'm going to discuss it later. Next, we can see we have a dot product, okay. The dot product of electric field and vector area, okay. So as I said earlier, this is the elementary area of the Gaussian surface or closed surface. The dot product can be replaced by, okay, simple algebraic product, that is EDA. So for this to hold, okay, electric field must be parallel to the area vector. So we need to note this, okay. Next, the integral, okay, this integral, the integral is 0, okay. This integral is 0 if electric field is perpendicular to area vector. So this is the third, okay. And fourth, electric field can be 0 on everywhere of the surface. Clear? So we have this. Now let us understand these conditions, okay, with reference to, let's say, infinite line charge. Okay, let's say we have a thin rod which is infinite in length, and let the rod contains positive charge, and charges are distributed uniformly throughout the length of the rod. Okay, so we have this. So we have infinite long thin rod, okay, containing positive charge which is distributed uniformly. Now, as I said earlier, in order to apply the condition of symmetry, okay, minimum one or more than one of these conditions must be satisfied. So we need to understand this. Now, we have a rod. Okay, this is a cylindrical rod, or it is a thin rod. Now, let us take point P at distance r, okay, from the conductor. So I can take another point, such point, at same distance r, okay. So I can take next point at distance r on this side also, at same distance, okay, at same distance r, at same distance r. Now, imagine this is a thin rod, and you have a point P at distance r on this side. You can take another point at same distance r on this side. You can take another point at distance r. Now, if you join all these points, okay, so let's say if you join all these points, okay, then you get a circle, okay, or you get a ring. Similarly, if you join this, okay, if you join next point, okay, which is at r distance, okay, if you join all these points, then you get a circle. So you get another circle, okay, and if you join all these circles, then you get a cylinder. So let me draw in this way, okay. This is a thin rod or cylindrical rod containing positive charge which is infinitely long. It is the same, okay. I'm redrawing in this. So what we get, as I said earlier, if we join all these, okay, circle, then we get a open cylinder. We get a cylinder, okay. If you join all the circles, then you get an open cylinder. So by symmetric condition, the surface chosen is cylinder, okay. The surface chosen is cylinder, and if we want to apply Gauss law, we must have closed surface. So we need to close the end cap, okay. So the end cap or caps must be closed, okay. So now we have a closed cylindrical Gaussian surface. So in this way, we select properly the closed surface, okay. Now we know we have now curved surface, okay. We have this, okay, and this is a line charge, okay, and the end are closed. So this is the curved surface. Now so this is straight, okay. Now this is closed surface. Now let us take a small elementary area, okay, of or on the curved surface, and let the magnitude of this area be dA. Clear? And we know electric flux or electric field lines from positive charge diverges out. So electric field lines is passing through this area, okay, as shown in the figure. Clear? Now we know from this expression, okay, let us draw a unit normal, okay, on this elementary area. So this unit normal gives the direction of vector area dA. So area of this elementary surface is vector dA, and vector dA and electric field, they are acting along same direction. So what we find? We find on curved surface, okay, on curved surface, we find electric field and vector area, they are parallel to each other. So condition 2 of symmetry is satisfied on the curved surface of the cylinder. Now let us come back to the end cap, okay. Now we have this, let us take a small area. I'm taking small area, and since this area is facing upward, okay, or we can draw unit normal. So we can draw unit normal, okay, in upward direction. So this unit normal gives the direction of vector area, and let us denote the area vector by the symbol dA, okay. So we have this. Now what we find, electric field is directed radially outward. So at the end cap, area vector and electric field, okay, they are perpendicular to each other. So I'm writing at the end cap, okay, at the end cap, electric field is perpendicular to vector area, because we know positive charge produces electric field in outward direction, and electric field is acting along this way, okay, it is acting along this way. So at the end cap, we find electric field and area vector, they are perpendicular to each other. So it means that flux through end caps, okay, both the end caps, this is 0. Clear? So we only get flux through the curved surface. So we only get flux through the curved surface. This is not 0, okay, this is not 0. So what we find at the end cap, we use this condition. Clear? We use this condition, and at the curved surface, okay, so if you look into this figure, okay, at the curved surface, so we have this is a closed cylinder, okay, at the curved surface, the magnitude of electric field, okay, the magnitude of electric field at each point, okay, the magnitude of electric field at each point on the curved surface is what? Constant. So we find this. So at this point, or on the surface of the cylinder, okay, the magnitude is what? Constant. So this condition is again satisfied. So in this way, we apply symmetry condition for line charge, that is infinite line charge. Now, let us discuss symmetry condition, okay. Now, let us discuss symmetry condition with reference to a sphere, okay. Let's say we have a positive charge distributed uniformly on the surface of the sphere. Now, let R be the radius of the sphere, okay. Now, since we have a sphere, okay, so we can select our Gaussian surface or closed surface to be sphere. So let us draw a Gaussian surface, okay. Which is a sphere, okay. This is a Gaussian surface. This is a uniform, okay. This is a uniform. So this is a Gaussian surface, okay. So this is not looking perfectly sphere, but keep in mind it is a uniform sphere, okay. Gaussian surface of radius r. Now, if we take a small elementary area on this Gaussian surface, let's say its area is dA in magnitude. Now we know electric field lines diverges out from positive charge. So electric field lines cross or passes through this Gaussian surface in radially outward direction. So we can take another small elementary area, okay. Now, let us draw a unit normal on this elementary area. Now, this unit normal gives the direction of vector area dA. Now, for this sphere, okay, for this sphere having uniform distribution of charge, at each point on this Gaussian surface, electric field is constant. So condition first is satisfied, and what we can see, okay, is that electric field is parallel to the area vector. We can see area dA is acting in outward direction, okay, and is acting along the direction of n cap, and n cap is unit normal. So vector area and electric field, they are parallel to each other. So condition 2 is satisfied. So in this way, we apply the condition of symmetric charge distribution, okay, in discussing the application of Gauss law.